네, 여러분 휴식 시간 잘 보내셨습니까? 네, 지금부터 삼성 보안기술 포럼 2부를 시작하도록 하겠습니다. 2부에서는 장영진 교수님의 키노트와 삼성 리서치 연구원들의 세션 발표가 진행될 예정입니다. 자, 그럼 네 번째 키노트 세션을 맡아 진행해 주실 삼성 리서치 이충은 마스터를 모셔보도록 하겠습니다.
안녕하세요. 삼성 리서치 시큐리티 팀의 이충은입니다. 오늘 네 번째 키노트 발표는 오레곤 주립대학교에 근무 중이신 장영진 교수님께서 발표를 해주실 예정입니다. 최근에 보안 분야에서 많은 한국 연구자분들 그리고 해커분들이 활발하게 활동을 하고 계시는데요. 장영진 교수님은 시스템 보안 분야를 주로 연구를 하시는 교수로서 그리고 실제 필드에서 활약을 하시는 해커로서 많은 두드러진 활약을 하고 계시는 그런 분입니다. 해킹에 대응하는 시스템 보안 기술, 시스템 보안 테스팅 기술, 그리고 조금 있다가 발표를 해주실 하드웨어 기반 보안 기술, 이런 여러 가지 분야에 대해서 활발하게 연구를 하시면서 최근에 세계 그 탑 보안 학회에 많은 논문들을 지속적으로 발표를 해주시고 계시고, 그리고 저희 소비자들이 많이 사용하는 굉장히 인기 있는 그런 제품들에 대한 흥미로운 그 해킹 그 사례들을 발표를 하시면서 많은 주목을 받으시기도 하셨고요. 그리고 해킹 분야에서 가장 그 권위 있는 해킹 대회인 데프콘 CTF에서 2015년, 18년도에 우승을 수상하시기도 한, 어떻게 보면 이론과 실제를 겸비한 아주 실력 있는 그런 교수님이자 해커이십니다. 2017년도에 학위를 받으시고 이제 교수로 재직을 하시게 됐는데요. 이렇게 젊은 교수님이시다 보니까 앞으로 활약이 더 기대되는 그런 분입니다. 그러면 장영진 교수님을 연결해서 인사를 나눠보도록 하겠습니다. 교수님 안녕하세요.
예, 안녕하십니까. 좋은 소개 감사드립니다.
예, 그 바쁘신 와중에 이렇게 발표를 맡아주셔서 감사드리고요. 이렇게 오프라인으로 오셔가지고 발표를 하시면서 같이 소통도 하고 그러시면 좋았을 텐데 아쉽게도 온라인으로 발표를 진행하게 됐지만 좋은 발표 부탁드리겠습니다.
예, 감사합니다. 화면이 잘 나오나요?
예, 준비됐습니다. 발표 부탁드립니다.
예, 시작하도록 하겠습니다. 그 발표는 영어로 진행하도록 하겠습니다. Good afternoon, folks. I'm Yeongjin from Oregon State University, and thank you all for attending my talk from the more than 1,000 miles away, and I hope you all stay well in this pandemic. And I also say thank you to Samsung Research First for inviting me to this kind of great event, SSTF 2020. And let's start the talk. As per the introduction, I usually play a role as an attacker in the cybersecurity field by hacking computers such as iPhone, Intel CPUs, or writing exploits for CTF challenges. But for today, I will talk about defense techniques that we can utilize for making our cloud computing secure. So to rephrase the title of this talk a little bit with the secret word, that is, I will talk about enabling confidential and private computing on the cloud using ORAM and TEE. And regarding this, let's start with the cloud computing first. Nowadays, we rely on many services on the server running on the cloud. For example, most of the mobile applications, their backend servers are hosted in the cloud, and not just for that, IoT devices, which usually has a very low computation power, offload their computation workloads to the cloud computing to utilize the fast, full-fledged CPUs available on the cloud. Moreover, many other devices, such as autonomous vehicles, drones, or even for vacuum robots in your home, they utilize this cloud backend to process machine learning data data collected from the massive number of the device and use back the trained model to enhance the device itself. And we can do this by having a private server, but the reason why we rely on the public cloud services such as AWS or Microsoft Azure is mainly because the elasticity of the cloud. That is, in case if our server gets massive number of requests by having more users or more devices, then we can easily horizontally scale the resource on the cloud. It's simple as just adding more resource. And we just covered the usefulness of the cloud computing. And let's get into the security about the cloud computing. Most services running on the cloud server protects data in transit, so meaning that the network data. And for this network data, we apply SSL and TLS encryption. That's some of the basic security mechanism that we can apply. And by doing that, no middleman on the network can read the data nor inject the data to the link. Next is about the data at rest. Cloud computing also has a disk on the remote site, and to store the data securely onto that, we may apply disk encryption. Then any attackers who don't know about the encryption key can never access the data at rest. So we just took a look at how to protect the data in transit and data at rest. With these two, our cloud computing looks secure. Then what's the problem? Let's take a different question. What about the runtime data? That is, this server on the cloud runs some of the program logic, and it uses DRAM as a data store for storing active and runtime data. And my question here is that, are these elements, logic and the DRAM, are these protected? Surprisingly, the answer is no. Although the current cloud computing protects the data in transit and data at rest, it does not protect the runtime data. Let's take an example. Suppose we would like to calculate 3 plus 5 over the cloud. I just take a simple example to explain the same example, to use the same example for introducing the cryptographic primitives I will describe later. Then we will send please calculate 3 plus 5 encrypted form over the network line. And then the server logic will decrypt the data and get the input as a 3 and 5 and calculate the addition, result 8, and send the result back. And to make it secure, we can apply encryption over 8 and send the data back to the client. But here, please note that such runtime data, number 3, number 5, and even the result 8, these are all unprotected. Then, why is that a problem? Why are we talking about the security of the data in RAM and CPU? Maybe you may not heard about that, the security of those data is matters in the operating system, or some other things will automatically protect that. But the reason for this is mainly because we do not own the machine in cloud computing. So think about who owns the machines in the cloud computing setup. This machine and several servers are not ours, and they are maintained by the third-party cloud providers, such as Microsoft or Amazon. And this creates some of the unique threat space in the cloud computing, which we will never observe when you use a private server. And this diagram depicts how we run the application over the cloud with a little bit of detail. So these cloud providers owns all the hardware, such as CPU, network, and disk, and that they will install the virtual machine monitor to make the server available for renting. And as a tenant on the server, we rent one of the virtual machine instance, install our favorable operating system, and then we install our server application and running at the application level. And then, as we just learned, we will connect to each client securely via SSL and TLS. And also, we store the data in an encrypted format on the disk. But doing such cannot protect the runtime data, so that's why I marked the application area as a red. So in this talk, something with the a green color is something secure, and something mentioned with the red color, meaning that it's insecure. And because we do not protect this kind of the runtime data, it lets attackers on the cloud who can control the virtual machine monitor, for example, administrator from the cloud provider side, or some of the malicious attackers who exploits vulnerability in the either operating system or virtual machine monitor. They can freely read and write all the data here because they are at the more privileged level. And this is an inherent problem of the cloud computing unless we protect this runtime data. But fortunately, we have a cryptographic theoretic solution to address this problem. That is so-called fully homomorphic encryption. And let's take a look at how this fully homomorphic encryption can protect the runtime data. Suppose we have a smartphone client with a secret key inside it, and it would like to calculate function f over some of the secret data. Then we will use the homomorphic encryption, which let us calculate over the encrypted data. And this is a magical tool. And to introduce one of the important property of the homomorphic encryption is that if we apply function f over the encrypted data, then under the fully homomorphic encryption, it will be regarded as the same as encryption of the function applied to the plaintext data. And to give a more better concrete example, do the calculation of the 3 plus 5, the basic example that we just took, instead of the 3 and 5 to the cloud server, what we can do with the homomorphic encryption is that we will send the encrypted data of the 3, encrypted data of 5. Then the server will calculate these two encrypted data, and then because of this property, it will result in as an encrypted format of the result 8. So with this, we first send the function f and the encrypted data to the server. And the server calculates function f over the encrypted data, and it will send back the result. And then let's take a look at what attacker on the cloud in this case. The attacker may observe the function f and the encrypted data, and also observe the encryption of the result, but the attackers may not access what is the data nor what is the result of the function calculation because they do not have the secret key. The secret key is only available at the client device. So on the other hand, at the client side, after they're receiving this result, because f encryption data is the same as encryption f data, if we just apply decryption, then decryption and encryption will be canceled out, then it will result in the f over data. And this is how homomorphic encryption works. And the cloud computing side will never learn about what kind of the data we just process. So the magical property of the fully homomorphic encryption let us calculate over encrypted data, and this naturally kills the attack surface of the runtime data on the cloud computing. But unfortunately, we cannot use this in practice for general computation because this is extremely slow. It is firstly invented in 2009, and it was several trillion times. Yeah, I'm not saying a joke. It was several trillion times slow at that time, and then it has been enhanced a lot. So nowadays, it's several million times slower than the regular execution. And what that means is that if you run a job that can finish it in 1 hour with a 1 million times slow for the optimal case, yeah, the job will end in more than 100 years later. So the implication here is that fully homomorphic encryption is good, but it is extremely slow to be used in practice. Then let's take a look at the flip side of the coin, practical defense. To protect the runtime data over the cloud, computer architecture designers, such as companies like Intel, implemented the so-called trusted execution environment. We call it as a TEE, as one of the implementation is Intel SGX. And what it does is that, so one of the problem was that in the cloud computing, cloud operators sits on the virtual machine monitor, they can do anything to our service. And to prevent that, Intel SGX first isolates applications memory space from the other programs, so that even virtual machine monitor, operating systems, or some other application cannot access this region of the memory. That's why I marked this area as a green one. Additionally, so this is prohibited, and additionally, to kill the attacks snooping data on DRAM, Intel SGX applies encryption for the data, the application data stored into the DRAM side, so the data will be scrambled like this, and thereby attackers on the cloud side will never read the data, even if they just snoop on the DRAM bus. And not to mention the other existing SSL TLS and the disk encryption can be applied to the same SGX case. So we can enjoy both all the encryption in transit, encryption at rest, and encryption at runtime. This looks great and seems like the problem solved. I have a good news and a bad news. And the good news about this is that this is fast. It only incurs like 10% of the performance overhead. This is much faster than fully homomorphic encryption. But this is imperfect to guarantee the cloud security because TEs, including Intel SGX, they are susceptible to access pattern inference attacks and also for the CPU side channel attacks. And I believe most of you have already known about some of the recent discovery of the hackers and researchers, many attacks targeting Intel SGX. And regarding this, let me show a very simple example of how an attacker on the cloud may infer the image data processed inside the Intel SGX without decryption, just observing memory access pattern. Suppose we run image processing in an SGX enclave like this one, and then suppose our logic in the Intel SGX to print either white or black color on the picture, it should access the upper block of the memory for the printing white color, and it should access lower block of the memory for printing black color. So this is a very simplified case, but the actual attack would be a little bit more complex than this, but the principle is the same. Then, an attacker on the cloud, although they do not know what is white, which is black, but if they apply a simple guess, the guess is simple. If the CPU accesses the upper memory, then just put 0. And on the other hand, if the CPU accesses the lower block, put 1 as a color. Then what the attacker may get is something like this. So these are not the exactly same with the original image, but this kind of result is quite enough to see what's being processed in the Intel SGX. And because Intel SGX targeting like a full protection over the cloud computing scenario kind of thing, but unfortunately, the implementation is imperfect and they are susceptible to this kind of attack. So let's summarize these two techniques. So fully homomorphic encryption crypto solution is too slow. TEEs, such as Intel SGX, it's fast, but killed by access parent inference attacks. Does this mean the end of the game? And we researchers love to tackle this kind of challenges. And because I'm not a cryptographer, I'm not on the side of like the enhancing the fully homomorphic encryption at all, but I'm on the side of the discovering potential solutions on the TEE side. So my question is, can we protect TEEs such as Intel SGX from this kind of the access pattern inference attacks? And regarding this, we have a great cryptographic solution called Oblivious Random Access Machine, and this is ORAM that defeats this inference attacks. So let's switch the topic to the question. Can we protect TEE using ORAM? And before moving to the next, let me introduce what is ORAM. And the objective of the ORAM is quite simple. It wants to kill any kind of the inference on the data via access pattern leakage. And it looks like difficult, but we have a very simple and naive solution. And what we can do is, suppose we have an array of memory like this, and suppose the case is like we need to fetch the data at position 2. And suppose there is an attacker on the DRAM bus spying all the memory access from the TEE. In such a case, if we directly access the position 2, then the attacker don't know which data I have accessed, but they know that I accessed the position number 2. So to kill this attack, what we can do naively is read the entire data and just keep the target data secretly in the CPU register. So in such a case, attacker will observe that we will read entire memory, but we can fetch this specific data securely. However, most of you have already noticed this is very inefficient because we need to read entire data, and data access for just accessing one element. So in the example, with 6 elements, so accessing 6 elements for the one item is okay. But think about our database is 1 terabyte. And if we just once reading of the 4 byte, but if we need to read the entire 4 terabyte of data, then that's a super inefficient solution. But fortunately, recently a set of cryptographers developed a new and fast ORAMs with the design of this kind of tree-like structure. So the family of this kind of tree-like structure ORAM is so-called the tree ORAM. And so the figure on the right side depicts a full-blown binary tree as an ORAM storage. And the ORAMs in the tree ORAM family, such as path ORAM, ring ORAM, circuit ORAM, developed in the 2013 and 2005, they do require O log n memory access. So it will be much faster compared to the OM. And let's take a look at how path ORAM works in a nutshell. Path ORAM basically splits the data storage into 2 parts, trusted part and the untrusted part. And because this kind of the theoretical ORAM is designed to be used in a remote client scenario, so you can regard this trusted memory side as like the smartphone, what that you owned, and the remote side, and you can regard this external memory, untrusted memory, as a storage on the cloud. And here we are talking about the path ORAM. A path here means that the set of the tree nodes starting from the new root to the leaf. And here, in a simple descent of the ORAM, we have a leaf node from 0 to 7. We have a total 8 paths, and path 5 means these 4 blocks. And then each node can store up to Z number of the elements, and then in this example, Z is 4, which is a practical parameter for the path ORAM. And because this entire storage is untrusted, and we can safely assume that we will apply the encryption from the trusted side to store each block of the data securely. And then a block of data can be stored into one of the path, and in the trusted side, this position map records which block is at which path. For example, the block 1 is at path 5, so it could be stored into anywhere in path 5, and block 2 is at path 7. Path 7 is this, so block 2 may reside at here, and block 3 is at path 0, and path 0 is this one. So block 3 can be anywhere in here. So this is the basic about the path ORAM. And for the next, we will take a look at how path ORAM can securely access the data over the cloud. Suppose we need to access a block 1. Then we first need to construct the position map, knowing that the block 1 is at path 5. Then we will read entire path 5 from the untrusted cloud storage like this. And because blocks are encrypted, so the cloud will know that we just read path 5, but they don't know which block we are interested in. And then we will store, after reading this block 1, we will store these data back to the same path. But if we just do that, block 1 will always be in this path. And if we keep reading the data on path 5, then the attacker can easily guess our interested data is on path 5. Then, how can the path ORAM prevent such kind of the inference? And path ORAM kills the attack by updating the path after having a 1 reading to the random one. For instance, we can select any kind of a random path from 0 to 7, and suppose that is 0. And then we update our trusted position map to 0, and then to preserve the property that the block 1 should reside on path 0. But we can only control this path 5, so we need to find some of the joint bucket between path 0 and path 5. And because the root node is only the joint node, so we need to move block 1 from here to there to synchronize the position map and the actual block storage. And then what we will do is we will encrypt, then write this back. So in the cloud storage, it will be moving from here to there, but at the cloud, it will see that we will overwrite the entire all the buckets, so they don't know that the block 1 is here. So this is how the path ORAM secretly accesses that it previously accessed path 5, but the attackers will never know that the same access block will reside on which path for the next. And here you might be curious about if this root node has already been filled with all 4 items. Then we cannot store block 1 at here. And that's why we have additional trusted storage, so-called stash. If this kind of node overflows, then it will store the data on the stash. And this is basically how path ORAM works. So in contrast to the naive ORAM that requires O(n) access, path ORAM just requires O log(n) access. And if we just take an example, for example, if we have a 4 terabyte storage and 1 billion elements, then ON access requires like accessing of the entire 4 terabyte of data for just accessing 4 kilobyte block, which is a total nonsense. But in contrast, because this kind of tree ORAM, path ORAM requires a O log n access, so here n is 2 to the 30, log n is 30, so it's just like something multiplied by 112 kilobytes, which is significantly less than 4 terabyte. So now it is something making sense for using this. Then let's take a look at how we can use ORAM for using cloud computing securely. On the left side, we have a trusted client, and on the right side, we have a storage server on the cloud. And suppose clients wants to access block ID 31337, then it will first consider the position map, and let's use the same example. Suppose the block is at path 5. Then it will send the access request for the path 5. So cloud server, and if there's an attacker, they know that we will read path 5. Then we will get the encrypted blocks to the client, and because we have the key, we can decrypt and access the block. And then we will update the path from 5 to something random, and then write back. And this is how ORAM, path ORAM prevents that the attackers might know this kind of the path number, but don't know about the actual path. And this path ORAM algorithm is protected with the theoretical bound of its failure rate, and the formula look like this. 14 multiplied by some of the small number powered by R, and R here is the stash size when overflow happens. And with a practical setup, we mostly use R as 80 or more, then the failure rate will be negligible, and this is how ORAM provides a proven security. And we just learned that the ORAM can hide the access pattern leakage. Then what an ORAM can do other than that? Because we can apply encryption to the blocks orthogonally, we can protect the confidentiality and integrity as well as the access pattern leakage. And because our ORAM can work confidentially and privately on the cloud, we can build a secure, very secure key value store on the cloud, which the attackers on the cloud will never know about what kind of data in the storage. And also using such a storage, we can actually build a database and run search on those databases, and that will build a searchable encryption. Next, let's get back to our main topic. That was how can we combine TEE and ORAM to protect the TEE? But I did not mention anything about the TEE while describing ORAM. But looks like ORAM can solely work as a means to protect the secure computing on the cloud. But the problem here is that this link, the link between the trusted client and this cloud server, this is protected by 1 gigabps network link at best if we assume the internet connection. In that case, a more important question to ask is O log n is small enough for this one? And let's do a little bit of calculation. Let's take the same example, 1 billion entries, 4 kilobyte block, 4 terabyte total storage. And a path ORAM, it practically uses Z as 4, so we will have read and write 2 access on the ORAM, and Z is 4, and log n is 30. 2, 4, 30, we multiply them all, then it will require 240 times more use of the bandwidth. That means if we want to just access 4 kilobyte of the data, then it requires transferring 960 kilobyte. And if we assume like a 1 gigabps link, it will result in just transmitting 0.5 megabytes. And this looks very impractical. Utilizing 1 gigabps link, we're just sending like 5 kilobytes per second. So implication here is that the ORAM is very slow to be used over the network in practice. So now we have another challenge. We started with the TE is fast but susceptible to access panel leakage. ORAM is resilient to the attack, but this is very slow. But in such a case, can you do something like cancel out bad things and then taking out some of the good things from each to build a fast and resilient to the access pattern attacks? And the answer is yes. And now we get to the main topic of this talk. And we can achieve this via crypto and system co-design. And let's take a look at how ORAM and TEE works together. So I just put that how the regular ORAM over the network works like this. And with the help of the TEE, we can actually put the trusted ORAM client on the cloud side. And the benefit of doing that is like we can protect the memory access of the Intel SGX using this path ORAM. And at the same time, the link speed, it was 1 gigabps over the network, but now it can utilize DDR4, which is at 341 gigabps. Yeah, much faster. And because SGX can run some of the secure computation, so we can just we retrieve all the path and we just retrieve the raw data and send back to the client. So this is how we can combine ORAM and TEE and make it fast and also protect from the attacks. So let's take an agenda of the crypto and system co-design. ORAM is slow. With the 1 gigabps link, we can just download 500 kilobytes in practice. But with the help of the TEE, we can boost this 1 gigabps to the 341 gigabps. Then we could speed up and utilize the entire 1 gigabps. 240 times slowdown and 340 times more bandwidth. It looks like very easy. Is it simple like this? Unfortunately, the answer is no. If it is simple like this, this may not be a research topic at all. Yeah, because this is not possible because this is there are many challenging things. And one of the challenges is that tree ORAM requires a trusted storage such as position map and the stash. And let's just take a look at the size of the position map. Suppose we have a 1 billion entry for a 4 terabyte storage, and suppose we just use 4 byte, 32-bit block ID. Then 4 byte, 4 billion times, then it will take 4 gigabyte just for position map. But the problem is that Intel SGX, it only supports encrypted memory for 128 megabytes. And if it goes over that memory size, then it will be drastically slowed down. So we cannot store 4 gigabyte of the data. And another challenge is that both position map and stash access must be oblivious, but in TEE, we do not have such trusted storage. Yeah. And one of the solutions is that we may apply ON access for these kind of the two data structure, but there are another problem. So we just mentioned that the position map size could be 4 gigabyte. Yeah. Then accessing 4 gigabyte entirely for the 4 kilobyte access, that's another nonsense. And then stash access. So stash is small, 4 kilobyte, 80 stash size. It's just a 320 kilobytes of the stash size. Size doesn't matter. But the problem is that we need to store all the valid blocks from one path to the stash. So the path has a level L Z blocks, which is a 30 and 4 in the 4 terabyte scenario. And then stash has 80 blocks. And to make it oblivious, we need to multiply all the vectors. And then it will incur 9,600 memory copies, and it will slow down the entire operation at that amount. So the challenge here is that we can enjoy 341 times speed up, but it will be slowed down 9,000 times. So this is a serious problem, and it also addresses the chicken and egg problem. TEE requires ORAM to protect its access pattern leakage, but the ORAM requires trusted storage, which TEE does not have. So one of the techniques to resolving this kind of issue is that we can bootstrap the trusted storage by having a naive ON access of the ORAM. So reading the entire data with the small amount of the data. I just mentioned about the small amount of data, then how can it store huge precision map, such as 4 GB? And to do that, we can apply the recursive ORAM. And before following the text, just take a look at this diagram first. And then what it does is, we have a ORAM like this. For the first case, it could be 4 TB, and it requires 4 GB precision map. Then we will put another ORAM as a precision map, smaller one, 4 GB, smaller one, 4 MB, and finally, we could get to the point that the precision map is small enough as a 4 KB, then we can use a naive mapping. And we studied about the enough theory and details, and for the next, let me introduce some of the recent implementation of the combination of the ORAM and SGX. I'm not going to go over the details of the paper, but just mention about the summary and the implication. The first work is Zero Trace, published in 2018, and it utilized both path and circuit ORAM and utilized the recursive ORAM to make the precision map small enough. And then protected the ORAM with TEE, and the result is the following. With the 10 million record available, and for transferring 8 bytes of data, they can transfer 6 kilobytes. And for 1 kilobyte blocks, they can transfer around 300 kilobytes. So although they build the good combination of the ORAM and TEE to make the TEE secure, but their performance numbers are far from the use in practice. And let's take a look at another work. Folks from the UC Berkeley implemented the work called Oblivious, published in the same year. And they realized that the storing of the precision map as a recursive ORAM, that's slow. So they designed the crypto to fit the requirement of the Intel SGX. And how they do that is, without using precision map, they build this kind of the virtual tree, and all the blocks are stored into some of the AVL, like a binary tree kind of fashion, and just store the root at the trusted storage. And then whenever they need to access a specific block, then they will need to traverse over the root, first child and next child. So it will require double O log square n access for the ORAM. And then result is around 3 times faster. So previously we talked about 6 kilobyte and 300 kilobyte, and now they can exhibit 17 kilobyte and 900 kilobytes. But still, it is not there for the practical use. And then last year, myself and my colleagues implement the work called the POSUP. And then what we did is enable the searchable encryption by using the similar structure of this kind of the virtual tree. And how we implement the search is we securely access one of the block in the ORAM, and that block will store the position of the next data. Then we will read the ORAM for the next data and next data again and again. And by doing that, we can enable secure searchable encryption over the cloud. But still, the performance of the just fetching 512 bytes, we get throughput of the 600 kilobytes, which is also far from the practice. And in this year, my colleagues and I thought about, because we previously just changed the ORAM to fit into the SGX. But how about the enhancing the system side? So we decided to utilize the multi-core to speed up the ORAM access. So specifically, we speed up the encryption and I/O access via the parallelization. So you can see the graph like this. As the number of core increases, then the data throughput goes up. And by doing this, we achieved around the 7 megabyte per second transfer, which is more practical, but still it's not there. So I just introduced several recent work pieces that enhance the ORAM in TEE or enhance TEE for ORAM, but still we are far from like exhausting 1 Gbps internet link. So the best we can get at this time was like a 61.8 megabytes. And the main reason that we cannot get to the like 1 Gbps link speed is like it's slow, stash access is slow, and encryption is slow, and Oblivious calculation in TEE is also slow. But please do not get disappointed. To overcome such a limitation, I would like to introduce another work in the same direction, which is called PRORAM, Practical and Resilient ORAM in TEE. But unfortunately, this is a work in progress that I'm doing with my colleagues. And the main question here is that with the ORAM and TEE, can we achieve like the exhausting all the internet link just for like the raw data transfer? And theoretically, the slowdown factor is 240, but we observed that like 341 as the like the bandwidth enhancing factor. I believe it is possible. So as a system designer, we take this challenge down as with the aggressive optimization and the performance engineering. That include bottleneck analysis, pipelining, optimization, and caching, and multi-core. So this is another type of the crypto and system co-design. Most of the others try to enhance ORAM to fit to the like the TEE, but what I'm doing is try to make the TEE to run the circuit ORAM or other operation at best. And to show some of the preliminary result with the same number of the zero trace, same setup, we could achieve like transferring like a 10 megabyte per second, which is 34 times faster than zero trace with an 8-core machine. And then what we are seeing is that PRORAM can enhance ORAM and TEE by 13 to 34 times. And we also run an experiment with the smaller size of the ORAM, around 100,000 record with the block size 48 kilobyte. And we achieved like transferring like 500 megabps, around like it's just a half of the 1 Gbps. And that means ORAM and TEE is available running a web server on an Azure Confidential Computing instance because that supports the Intel SGX. That's possible. And another good thing is because we enhanced the ORAM, so all the other work that works on such application can enjoy this kind of the performance improvements as like 34 times. So, and as final remarks, let me introduce some of the future directions of like this kind of the crypto system co-design. So I just retrofitting the operating system or other system primitives to support ORAM better. But for enhancing TEE, we can also change the hardware for putting some of the trusted memory in TEE or developing Oblivious instructions which can run ORAM faster. And that's the one of the direction. And another direction is that design the ORAM protocol to consider the system level restrictions, for example, that Intel SGX has. 128 megabyte of the trusted memory and having no Oblivious memory. And another direction could be, we just observed like a combination of the TEE and ORAM, and we can make it to be interplay with the TEE with the multi-party computation or TEE with the fully homomorphic encryption. In summary, today I introduced techniques to combining on ORAM and TEE as a crypto and system co-design, and as a secure mechanism for using cloud computing secure. And the symbiosis of ORAM and TEE, we take the fast element from TEE and then killing the access pattern inference attack from the ORAM. And by combining that, we can build fast and resilient computation on the cloud. Although what we are doing is a little away from enabling the truly confidential and private computing in general, I'm seeing that such a future will come soon and hope to see many more works in this crypto and system co-design area. And this is the end of my talk. Thank you for your attention, and I'm happy to take any questions from the audiences.
예, 교수님 발표 재밌게 잘 들었습니다. ORAM과 TE의 조합을 활용을 해서 클라우드 서비스에서 효율적으로 데이터를 보호할 수 있는 그런 방법론을 말씀을 해주셨는데요. 시간이 좀 많이 지나가지고 질문을 한 가지 정도만 드리도록 하겠습니다. 이제 발표에서 클라우드 서비스에서 사용자가 쿼리하고 리스폰스하는 그런 그 유즈 케이스를 상에서 이제 위험 모델링을 하고 그 제안을 해주셨는데, 예를 들면 뭐 클라우드에서 데이터를 대량으로 모아놓고 배치 프로세싱을 하고 리스폰스를 하는 그런 상황으로 좀 그 문제의 범위를 넓혀보거나, 아니면 조금 더 넓혀서 뭐 단말에서도 이런 접근 방법을 활용하는 것이 유효할지, 그런 거에 대한 좀 의견을 좀 부탁드리겠습니다.
예, 우선 그 많은 양의 데이터를 하나씩 이렇게 하는 게 아니라 전체를 이렇게 배치로 넣어놓고 이제 액세스하는 걸 말씀하셨는데요. 그 부분에서 이렇게 인텔 SGX와 ORAM을 붙이는 게 가장 합리적인 선택입니다. 그 이유가 이제 데이터가 일단 그 클라우드 서버에 다 올라가 있다는 거잖아요. 예. 그럼 그 상황에서는 이렇게 그 액세스 패턴을 숨기기 위해서 Oblivious 액세스를 이렇게 하는 게 그냥 그 DDR4 DRAM 뭐 이런 그 스피드로 가능하기 때문에 저희가 하는 연구랑 똑같은 스피드로 이제 데이터를 처리할 수 있기 때문에 이제 배치 프로세싱에 이제 이게 좀 더 적합한 모델이고요. 두 번째 질문이 뭐였는지 한번
클라우드 서비스를 그 가정하고 말씀을 하셨는데, 혹시 뭐 단말이나 다른 환경에서도 이러한 사항이 문제가 되거나 이 활용할 수 있는 뭐 이런 어프로치가 될지.
예. 저 단말에서는 제가 지금 생각할 수 있는 거는 그 요즘 CPU 사이드 채널이 되게 위험하지 않습니까?
네.
예. 그런 경우에 오블리비어스 액세스 자체가 메모리 액세스 패턴을 모르게 하는 거기 때문에 사이드 채널 어택이 이제 그 메모리 액세스 패턴을 공격하는 그 형태라면은 저희가 이제 ORAM을 적용함으로써 그런 공격을 이제 펀더멘탈하게 막을 수 있습니다.
네. 예. 발표 오늘 그 흥미로운 그 발표해 주셔서 감사하고요. 질문에도 이렇게 성실히 답해 주셔서 감사합니다. 예. 감사합니다.
예, 감사합니다.
네, 감사합니다. 키노트 네 번째 장영진 교수님의 발표를 들어봤습니다. 진행에 도움을 주신 이충훈 마스터님께도 감사의 말씀을 드립니다. 보안기술 포럼 어느덧 마지막 세션을 이제 진행할 시간이 되었는데요. 이번 세션은 삼성 리서치 시큐리티 팀에서 준비를 했습니다.